So continuing on from the last lecture, we're going to look at what happens when we apply voltage to a MOSFET. We looked at already what VGS does. The gate to source voltage creates a channel once it gets up to the threshold voltage and there's current flowing. And until we apply a voltage between the drain and the source, we don't have any current flowing. So we're going to start out by applying a small voltage at the drain. So it's right over here. You've got a voltage source. Remember, there is no current going into the gate, but there is current going from the drain to the source, and it goes through that induced N channel that we created before. So there is current that flows. If we look at the relationship when we have a small voltage of VDS, and this is pretty small, there is a conductance of this channel, and it will change depending on how far above the threshold voltage you are. So if VGS is less than threshold voltage, we have no current, and we know that. If VGS is above the threshold voltage by one amount, we get a linear relationship there. If we change the amounts, we get different values, and that should have a plus right there. And if we look at the slope at any given point, the slope of that value is the conductance of the channel at that time. And this is something that can be calculated later. We haven't talked about Kn prime yet, but you notice that the width and the length of the device features what the conductance is, which makes sense because that determines the space of the particular channel flowing area. So as we make VDS larger, the channel begins to get bigger at the source, but not at the drain. And ID gets bigger, but the relationship becomes nonlinear. So eventually, as you increase VDS more and more, the tapering is so extreme that the N channel actually pinches off at the drain end. And we have the maximum amount of drain current we can get. And if we increase VDS more and more and more, we don't get any more current. However, the question that I always had as a student that nobody answered was, if it's pinched off, that sounds like the current goes away, and that's not what happens. The current just stays the same. The reason for this is because the electrons, remember the electrons are going the opposite direction of the current, they go into this big funnel, and then they kind of drift across that depletion region. So they're swept across because there's a positive charge that keeps them moving. So that's one of the weirdities of semiconductors, is that the electrons go in the big end of the channel and then they just get swept across the depletion region. So the current can't increase, but it can stay the same. So as we increase VDS above the overdrive voltage, we get the pinch-off value, and the current is nearly constant. And again, this is just stuff that I kind of already said. This is known as the saturation current. This is the current that happens basically, if you think about it, it just can't take any more current. So the saturation current is the amount of current that is flowing when it's kind of full, when the region is pinched off and you can't have any more. The MOSFET actually works in two different areas of its operation. It can operate when VDS is above VOV, so it's above the overdrive voltage. That's in the saturation region. So that's just what we were talking around, where the drain to source voltage is such that the current is really going to stay constant, and if you increase VDS, it doesn't matter. And then if you have drain to source voltages that are less than the overdrive, you're in a different region. You're in something called the non-saturation or triode region, and it's called both things. In engineering electronics, it's always called triode region, and then in this class, it's always called non-saturation for whatever reason. So this is how the curve works when we're looking at the operation of a MOSFET transistor. For values below the saturation value or the overdrive value, for VDS values, you start out at the beginning at kind of an almost linear relationship. And that was the point when VDS was really small. You get kind of a linear value. And then as we move, the curve bends because the increasing VDS increases the resistance. So the resistance doesn't stay the same. Because it doesn't stay the same, the curve has to curve. And then in the saturation region, pinch-off occurs, so VDS doesn't affect the current. There is current, but it's not affected by changing the drain-to-source voltage anymore. So the value of drain current saturates when we reach that value of VGS minus VT, and we can actually find the value of current if we know these parameters. Now we'll know VGS, we'll know the threshold voltage, we'll know the width and the length, but what's Kn prime? What is that? Kn prime is something called the process transconductance parameter. Fancy name for just something that takes into account the capacitance and the mobility of the charge carriers. So the mobility of the electrons at the surface, which is going to be different, and you're not ever going to have to calculate it. It's just different. But sometimes those constants, because we can find the transconductance parameter relatively easily, sometimes they are combined into something known as the conduction parameter, which is a capital K sub n. And you can see the equivalencies at the bottom. Sometimes it's used just to make things less messy when you're dealing with equations. So that is the relationship between the width, the length, the transconductance parameter, the conduction parameter, and the capacitance in the channel. Then we can find the drain current in the non-saturation region in a different way. Because remember that the drain to source voltage is going to affect the current, and it's going to be a curve. So it ends up being a polynomial kind of relationship, which again has its couple of alternate forms there, depending on how it's calculated. But it really functions pretty much the same. If we were to take the drain current and the gate to source voltage, and we held VDS constant at a small value, not a big value, we could actually plot those values of VGS, and we can actually extrapolate that curve down to the x-axis and find out what the threshold voltage is. This is something you will actually do as part of the semester project. This is, you will have the data, you will plot it, and you will extrapolate a line down to where it intersects with the x-axis, and that will give you your threshold voltage. A p-channel MOSFET, pretty much exactly the same. Everything just goes in the opposite direction, so I'm going to go through them kind of fast. The induced channel is the same. The process conductance parameter is the same. One of the things to note is that the mobility of electrons in the valence band are different than the mobility of the electrons in the conduction band. And generally, valence band electrons have a lower mobility, which means that the process transconductance parameter is going to be different in PMOS devices. So the WL ratio has to be increased in order to get the same transconductance. So that is something that is part of, if you have a N substrate with a P channel, that is a difference between them. It just has to do with the mobility of the electrons in the different environment. We also have something called CMOS, which, no, you don't really have to remember or be tested on this. You'll just see it again later, and that's what it is. So if you've ever heard of CMOS, it's just NMOS and PMOS stuck together. And I'm not going to explain it right now. I do explain it in engineering electronics a little more, but not much more. So that's just another type of device you can end up with NMOS and PMOS values and circuits. The circuit symbols look like this, and in this class you most of the time won't have to know the circuit symbols. And then these are just ID versus VDS characteristics summarized for the NMOS value. So this is all the calculations you would have to do to kind of find the values that you would need. Most of the time in this class, we don't talk as much. We do talk a little about the non-saturation region, but both regions are valuable. And then when you actually plot the whole ID versus VDS characteristics, and this is another thing you will do in the semester project, there are all sorts of parameters that go into determining where these curves come out. These curves do look just like the first one I did, which was just for a specific value of VGS, but when you change VGS in steps, you get this family of curves, and you'll notice that there's a red dashed line, which is the dividing point between the non-saturation and saturation regions. And that is at the point where VDS equals the overdrive voltage. So those occur at those points. For PMOS, the equations are slightly backwards, and I will tell you that one of the biggest issues that students have is just remembering to get the polarities right, which means I may basically never ask you about PMOS stuff because it's just too easy to get all the polarities confused. So you do need to know what they are, but I don't tend to ask you too much about them. We touched on transconductance earlier and talked about how when you take a small value of VDS and then you change the values of VGS, you get a slope, a linear slope, that gives you the conductance at that particular value. We actually look at the conductance over the whole curve, and remember the ID equation is different depending on if you're in saturation or non-saturation. So for non-saturation, the ID equation, when the derivative is taken, we get a transconductance that only depends on VDS and is a linear equation. Notice VDS is not squared or anything, so it's just a linear equation in non-saturation. In saturation, VDS has no effect on the transconductance, and it increases linearly as VGS increases. So those two kind of go together, and they are different depending on if you're in saturation or non-saturation. The last thing we're talking about is that fourth connection, the body connection. You can't have the source and the body at the same voltage potential. And zero, of course, is the same, but they can't be negative. So the source and the body have always been shown connected to ground. And if the source body voltage goes up, then the threshold voltage goes up. And the gate to source voltage would have to go up to increase and reach the same value of saturation current. That's basically why it's oftentimes just connected. This just shows how if you were to increase the voltage difference between the source and the body, so if it's 1 volt, 2 volts, or 4 volts, you notice VGS is going to go up. And as it does, you'll notice that the threshold voltage, which is marked in blue at the bottom, increases for increases in the source body voltage. This is not something that is going to be calculated. It's just a conceptual idea. So that's all we have to say about that. And that is all we have to say about MOSFET.